Okay, so we're here to talk about tensions in cosmology, and I thought I would inject a little bit of positivity into the story, and I'm going to talk about a tension that actually went away, right? So this is just for us to remember that things might look complicated right now, but we will find solutions to whatever our tensions actually are. So the topic is going to be time dilation of high redshift quasars. So I'm going to give a very brief background, a little bit of history, and then talk about the main topic, that is quasars. So I don't have to tell this audience about our cosmological model, right? The expansion of the universe. We all see this in our cosmology class, and we all know that our view of the distant universe is basically redshifted. The expansion of space redshifts photons. And the question is, what is the implications, the physical implications that we're going to get due to this expansion of space? Now, if we think of our photons as coming from little oscillators, right? As the wavelength gets longer and longer, that means that we should see those oscillators oscillating more and more slowly, right? So what this tells us is that when we look back into the universe, the fact that we are seeing redshifted light should mean that we see cosmological time dilation, that we should see the distant universe run in slow motion compared to today. Now, of course, this is not a new story, right? This is something that we've known about for a long time, and this was proposed back in 1939, that one way of measuring this cosmological time dilation is by using supernova, right? Supernova explode, they brighten, and they fade away, and in that time scale of them brightening and fading, if we have distant supernova and we compare them to nearby supernova, the ones in the distant universe should appear to brighten and fade over a longer period than ones in the local universe. And it's a reasonably strong effect. It's proportional to 1 plus z. That's what you can get from your standard cosmology textbooks. But I think it's also worth looking at how big the time dilation factor is going to be as a function of look-back time, because what you can see is that z dependence turns into a very nonlinear dependence in terms of look-back time. When we look back over the, a few billion years, that time dilation isn't very big. But as we look back further towards the Big Bang, then the time dilation factor formally goes to infinity when t goes to 0. So if we can see the very, very distant universe, we should see it tick by in very slow motion. Now, of course, this prediction was made in 1939. It took a few decades for people to be able to measure this particular time dilation, and that's because of a couple of things. Okay? So firstly, what was discovered is that, of course, not all supernovae are alike. Okay? Your starting assumption is that every supernova explosion is basically identical. And of course, in astronomy, what we do is we go out and we look at these things. We find that A is not like B, and we start to give them their own little boxes, type 1a, type 1b, etc., etc. So it took a number of decades for people to get appreciable supernova samples, and when they had those samples, they could basically hone in on the type 1As as the ones being the most similar in terms of their explosions. And of course, we now tie it down to a particular mechanism where matter has been poured onto a neutron star or white dwarf star. From a more massive star, you get to a critical point, you get an explosion. But again, even in that subclass of 1As, they're not actually all identical. Each supernova has its own peculiarities, and it was only through a huge set of work through the 1980s and into the 1990s as part of the Cosmological supernova project that people realized that you could account for these differences and that you could put these supernova onto the same sort of framework, right? You could basically make supernova standard candles. So again, this is the part of history, of course. It was at the end of the 1990s with these supernova samples that people realized that we were living in a universe with an accelerating expansion. So we have the presence of dark energy. But of course, on the flip side of that picture there, that standardization of supernova meant that you could now actually use them as clocks as well as standard candles. So you could basically look at the time it takes for each supernova to explode and fade, compare nearby supernova to distant supernova, and measure the cosmological time dilation. And so, again, this paper is very recent, right? This is only 2018. What you've got here is basically, they call it the aging rate. This is basically how slowly a supernova is brightening and fading. Here we've got the nearby supernova. On that side, we have the more distant supernova, and the more distant supernova are brightening and fading more slowly compared to those nearby. And not only that, we have this 1 plus Z relationship, which we expect in our time dilation. We get precisely that. So, of course, people are very, very happy, okay? So the samples are getting bigger. We seem to be identifying the expected cosmological time dilation. So this is some of the more recent work that was done using the DES survey. So what we've got here are basically 1,500 supernova. They're observed in different bands from short wavelength to long wavelength. These are the light curves of the supernova, right? They've already had that 1 plus Z term divided out. Everyone just assumed it's going to be there. And so essentially, if you take a look at the far right column at the top, so that's a higher redshift supernova. So it's been observed at shorter wavelengths. You can compare it to the supernova we've got in the lower left. They're basically in the same rest frame, and their light curves are the same. And we went back and we analyzed all of these quite recently, and you can measure what that factor is, and it's basically 1, precisely what we expect. So everyone's happy, right? I mean, there was no tension there to start with, right? Essentially what we have cosmologists celebrating. We find the universe is doing exactly what we expect. Except there's a problem. And the problem is that supernovae are not the only variable sources in the universe. So what I want to talk about are quasars. So quasars, of course, are supermassive black holes surrounded by matter. They're swirling at relativistic speeds. They're exceedingly bright. We can see them way back to the edge of the observable universe, and they vary. They vary in brightness. Now, even when I was a student way back in 1990, people were already complaining is that you look at quasars and they don't seem to do what cosmology tells them to do, i.e., we should expect distant quasars to vary more slowly than nearby quasars. Okay? Should be a cosmological time dilation. So these are just some example light curves that we get for our quasars, and we can already start to see what the problem is, right? So these are just different quasars from, I don't even remember the source of this, but they go out to relatively high redshift. You can see that there are variations going on in those light curves, but they're not simple. So unlike a supernova, which just brightens and fades, a quasar, basically the accretion disk, has got lots of complicated processes. It's basically got its own weather system. Its energy is being released in bursts, etc. So you get this very strange kind of variability. But the cosmological aspect should still be there, right? It's whatever intrinsic variability we have, on top of that, there should be this cosmological 1 plus Z. Now, things really took a turn back in 1993 by a paper by Mike Hawkins from Edinburgh Observatory. So he had been using the Schmidt telescope in Australia. So for the younger generation, a Schmidt telescope has a large field of view. You could put a big photographic plate there so you could survey a large region of sky. And they'd been doing that all the way back before the early 1970s. And so they had built up a basically series of deep images of particular regions of the sky. And Mike Hawkins had been focusing on a particular region and identifying quasars and measuring their variability over timescales of basically 30 years. So he had all of these different light curves for several hundred quasars. And I'll just put this paper up. This is from 2010, because this one caused the real problems. He basically did statistical analysis on his quasar light curves, essentially measuring the power spectra. And essentially, he split the samples up into low redshift and high redshift and measured the power spectra. And that's what you get on the left-hand side here. So those dots there are the two samples. And you get that the power spectra lie on top of each other for both high redshift and low redshift quasars, which says that they have the same properties in their variability. If you introduce a 1 plus z term and ask what's going on in the quasar frame, then those data points actually separate out, which is the opposite of what you would expect, right? You'd expect that if there's something intrinsic going on, you put in the 1 plus z, that should bring these two data sets together. In fact, it separates them out. So again, there's been a bit of argument about all of this. Mike's proposal, which he started back in 1993, is that the variability of quasars is not intrinsic. Right? We've had this notion of quasars being supermassive black holes, accretion disks, etc., since the 1960s. He says, nope, that's wrong. They are luminous sources. They might be quite distant, but their variability is due to external effects, due to microlensing. Now, not many people took this very seriously, but just following on from Dan's comment about the general public, we might think this is clearly a little bit crazy. The general public love these stories, right? So back in 2010 with Mike's paper, these stories started to appear that quasars don't show the expected time dilation, and therefore cosmology is wrong, cosmologists are idiots, the usual kind of stories that you get. So, do we care? I said this has bothered me since I was a student, and I tried to get hold of Mike's data to do an analysis with it, but he wasn't parting with it. So, a couple of years ago, though, things changed. So there was this paper by Zachary Stone whereby he published the photometry of 190 quasars observed in stripe 82. Okay, so these quasars were identified way back when with SDSS, but they have been monitored by a series of telescopes ever since. So there's 20 years worth of light curves. They're not wonderfully sampled, right, because they're different telescopes, etc., but they've been trying to put them all on the same sort of footing. They've been observed in multiple bands, and importantly for what we want to do here is that by the time this had come out, there'd been some advances in understanding quasar light curves, and it was realized that there is a pattern to their variability, right? And that pattern is that they're underpinned by a damped random walk. So it's a particular statistical kind of variation, but there are time scales written into that information. So they take their light curves, they go through a whole bunch of analysis, and one of them is to estimate what this damped random walk looks like, what its parameters are, and importantly, you have a function that basically gives you the correlation between points in your light curve, and that has a time scale in there. So that tau damped random walk, we said, well, what if we use this as a tick, a clock, right? We'll use this as some kind of measurement of the intrinsic time scale of what's going on. The big problem that we have, again, is that we've got 200 quasars here. Quasars come in a whole range of varieties, some bright, some faint, etc. So we need some way of basically putting like quasars with like, and this is essentially what we had. So remember, each quasar was observed in 3 bands, so every quasar on this plot appears as 3 points. What we're seeing here are the quasars as a function of the rest wavelength of their observations. So we take out that 1 plus z in their wavelength. On the side, we've got their bolometric luminosity, and we basically just group them, okay, into the boxes that you can see. And we essentially just say to ourselves, right, if we take one of these boxes, then we're looking at quasars of a similar intrinsic luminosity at a similar rest wavelength. Let's assume that their variability is similar. So they will all have some sort of similar kind of damped random walk timescale. But these damped random walks, these are the observed damped random walks, and so any variation in any little patch, the only thing that's left to vary is the cosmological aspect. Okay? So essentially what we have is that we take any one of those, we have that there's an intrinsic timescale given by that CK plus the cosmological term, and that gives us the distribution we have in each of those. So you go through, you do your standard Bayesian analysis, we test a bunch of hypotheses. We've basically firstly set n equals to 0, that there's no cosmological dependence. That's the kind of picture that Mike Hawkins was proposing. Your timescales of your variability come from matter in between. It's got nothing to do with the source. So we shouldn't expect there to be a cosmological effect. We fix n at 1, which is our cosmological expectation. We allow n to be a free parameter, etc., etc. And you go through and you measure the Bayesian evidence. And what you get to a very high degree is that your hypothesis that n equals 1 is the best hypothesis given the data at hand. So the cosmological expectation is basically what the data returns. The option where n is equal to 0, that there's no cosmological dependence, essentially that is highly downweighted compared to the cosmological case. So that's good. If we consider the case H2, where we allow n to be a free parameter, then we get a distribution which is quite broad, but it encompasses n equals 1, and the cosmological hypothesis appears to be supported. So at some level, that's good. That means that tension, that the fact that quasars weren't behaving the way we expected, really came down to essentially the data that was being used. What we didn't have until recently were enough quasars with sufficient duration in their light curves and enough sampling that we can actually pick up the statistical features which we can latch onto as that particular tick in the time scale. So, of course, it's not centered at 1. It's quite broad. Why is it quite broad? Well, it's probably quite broad for a couple of reasons. Number one is that we had a very coarse kind of model. Number two, there are other factors that are likely to be at play, right? So there's going to be potential evolution in the source populations, etc. We have to remember that the most distant quasars that we have in our sample go out to redshift 4. So we're looking back over 10 billion years, and we're asking the question, is a quasar at redshift 4 the same as a quasar effectively today? All right, so there might be evolutionary effects. And we did basically explore this by looking at our intrinsic parameters, and so these are for a range of boxes that we have. There is a systematic variation which is suggesting that there is an underlying kind of model there, but our model there was particularly coarse. So what we did more recently is we essentially just reparameterized everything. So essentially took the key parameters, the bolometric luminosity, the rest wavelength, and instead of binning things up, you can construct this this surface. So it's linear in the two terms, plus there's a cross term that gives you any other variations. Plus then we have our cosmological term. Again, we go through, we do basically the same kind of analysis. So again, this is now the entire quasar sample, again with the wavelength versus bolometric luminosity. Underneath that color, that is that surface. That's the best surface that we have to represent our data. And so it does what you expect it to, right? The more luminous quasars have shorter variability timescales, etc. We go through and we measure all the parameters, but the important one down there is that our n is now 1.14 plus or minus 0.34. So it works. We still have a little bit of width to our n distribution. Again, it's not centered at exactly at 1, and that's probably because our model is not a fantastic representation of what's going on in quasars. It's probably somewhat more complicated, and we're working towards that. But I think really what it reflects is that as of yet, we don't have a large enough data source, right? We have 190 quasars rather than 1,500 like we have with supernova. They are complicated things. We want to cover more of this particular space, and we probably need to observe these objects for multi-decades before we can be certain what these timescales actually are. So I'll just wrap up with the conclusions. The conclusions are that there has been a claim that quasars were being kind of cosmological bad boys and just not doing what they were expected, but underneath the variability, there is a cosmological signal. It's just more complicated than people expected. So the situation we have at the moment is that we don't really have sufficient data to tie down the underlying variability to a level that we think that we have it completely in the bag. But it does hint that there is something going on that we can get to grips with. So when we have large enough quasar sources such that we can really understand the variability physics, then we will have the opportunity to probably standardize quasars the ways that we did with supernova. And so it has the potential in the future, these will be useful cosmological probes. And I'll finish there. So thanks.
Thanks, Geraint. That was really interesting. One thing I just wanted to get you to clarify because I didn't understand. You said that when you had the larger sample of quasars, you're able to run your damped random walk analysis, you get your constraint on n, and you implied that the earlier analysis that used fewer sources and found an inconsistency with what we expected from cosmology wouldn't return n equals 1 if you ran the same analysis again?
No, so I'll just correct. So the original sample from Mike Hawkins from the Schmidt telescope is not public. And I've tried to make it public, but I haven't been able to get hold of it. So I can't tell you what that data set would say.
That was really, really interesting. So I have two questions, actually two clarifications. The first one, how you define bolometric luminosities, because it's for quasars, most of the luminosity is in a range where you don't actually see it, especially for relatively coldish accretion disk, like low mass black holes. And the second question is, how do you define your quasar sample?
Okay.
How is it selected?
Yeah. So this is great because neither of those things is something I decided. So the sample was chosen from Stripe 82, and it was quasars that they picked out way back when they were doing SDSS. So they identified these objects, and they got their redshift. So it was a Sloan selection on those objects. For the setting of the bolometric luminosity, that is one of the things that Stone does as part of the data release. So we took their bolometric numbers. Now, if there's a different way of doing that, we'd be happy to incorporate it. But what we didn't want to do was say we took the data and then we massaged it and then we did our analysis. We just want to take the data and apply it as it was.
Okay, an outsider's question. It seems obvious to me that the average supermassive black hole should get more massive as cosmological time passes. And I'm sure you know the masses of each quasar that you observe, but how does that evolution change what is observed?
Again, they determine the black hole masses as part of the analysis that they presented. We did actually use those. We did several steps in the paper where we brought in those additional properties to see how they influenced the Bayesian evidence that we got, and we found that they had no effect whatsoever. The key thing was the bolometric luminosity, because the black hole mass is correlated with the bolometric luminosity, so we took the observable and used that. But where we tried to bring in the other parameters, they had no positive effect on the Bayesian evidence that we were calculating. And that's either because they have no effect, or the data's just not, it doesn't have enough constraining power to say that, yes, this is an important aspect.
Thank you for the great talk. So are there any other observables apart from quasars and supernovae that we can see this effect?
Depends who you talk to. So that people are, there are other variable sources where people are wondering if you can use them as a standard clock. So there's both fast radio bursts and gamma ray bursts. But similar to quasars, it's do we understand the source population at a level where we can say what the intrinsic variability should be doing. So people have searched gamma ray bursts for a 1+Z signal. They say they see it, but error bars are really, really big, and it's the uncertainty in the physics that's the real problem.